Okay, so we are ready to move into the last type of mechanism that we're going to be designing, and that's going to be a crank rocker mechanism. So up until this point, the first kind of main two sections that we've been looking at were slider crank mechanisms. We looked at inline slider crank mechanisms as well as offset slider crank mechanisms. Now we're going to go into the last type, like we say here, it's going to be a crank rocker. So a crank rocker just means that instead of a slider being linear on our output like we've seen in the previous two types, we're now going to be seeing on our output, link number 4, it's actually going to be oscillating back and forth. We've seen many of these kind of in the early parts of kinematics here, but now we're going to be looking at how do we do that reverse engineering or that designing from the function. So let's take a quick peek at the basic mechanism animation here. It's a little YouTube clip. Yes. There we go. So as we look here, the crank is on the right-hand side, and then you'll notice that the oscillator or the rocker that's going back and forth, which is link number 4, is going back and forth through an angle, okay? And as you know, we call that the throw angle. So when we're looking at a linear slider crank, I'm gonna this up here. We'll start back over. We'll look at it again. As you know, with a slider crank, we call the output the stroke, where when we have something that's oscillating, the angle that it goes through is going to be the throw angle. So we're going to be looking at mechanisms like this in terms of, designing those like we did for the slider cranks. So I'm going to stop that one here, hit escape. And I think I have one more. This is a windshield wiper. Um, so again, you'll notice that we don't have linear motion on the output. Instead, we have that oscillating, and that would be a typical windshield wiper application for a 4-bar mechanism. So a nice little short one there. See, get rid of that. Okay. So as we look at a crank rocker mechanism, as we mentioned, the throw angle is going to be that angle at its extremes for what we want the function to be. So in the case of a windshield wiper, we would probably look at the windshield itself and try to figure out what is the angle that we want to sweep in order to get, it cleared so that somebody can, see out of it, depending on the weather that's going on. So your throw angle is going to be that angular displacement. And we're going to be looking at in terms of the C1, C2. So just like we did with the slider, the C values were at the center of the slider going back and forth, which was on link number 4. This is now going to be at the top, if you would, of our oscillating or rocking link so that we can measure between those two. Now, the crank rocker can be used as a quick return mechanism, as we saw with the windshield wiper as well. And then the little note here that we want to be aware of is that the radial length between the two extreme positions is going to be 2 times the crank length, okay? So that's going to be something that we're going to want to add as a condition for the crank rocker mechanisms. I just want to go one more further here. This is the procedure. So what I want to do is I want to add to our equation sheet. I'm going to go underneath here. We want to add a section here for crank rocker. Okay. And we're going to add some of these items like we did for the other two. So for a crank rocker, all right, we know that the throw angle is going to be the extreme positions of link number 4. Link number 4. So it's going to be that oscillating link. What are the extreme positions or the angle that it's going to go through for its output? Okay. Now, something we have to consider, we're going to have to now know what the length of link number 4 is going to be. That's going to be the output link. So when we had a slider crank mechanism, the slider was just going back and forth. There was a link number 4, but it was along a linear path. Okay. So there wasn't a length of that link. But in the case of the rocking link at the end of our mechanism, that's going to be the length number 4. That is going to be assigned by the designer, okay? So that's going to be something that you're just going to pick, and you're going to see that in the example that we do, okay? Now, if we go back to the statement right here on our PowerPoint presentation, okay, it says the radial length between the two extreme positions is going to be 2 times the crank length, okay, 2 times the crank length. So the crank length we know is going to be L2, okay? So we can say underneath here, L2 is going to be equal to the radial distance. It's going to be C1 to C2. Okay, it's going to be like that distance between those two from C1 to C2. It's going to be a length, okay, divided by 2. Okay, divided by 2. So half of that distance. So what are we talking about? So if we go underneath our camera and we look at figure 5.6 on page 116, okay, at the top here we see a crank oscillating mechanism. So the crank is right here, and then link number 4 is going to oscillate back and forth, okay? Notice that the end of link number 4 is point C, and its extreme position furthest away is the C2, and the closest position along that throw angle is C1. So what they're just talking about just now is if we go down here and we just take a straight line between C1 and C2, this distance right here, all right, is what they're talking about, all right? And this distance is going to be equal to L2 times 2, 2 times L2. So what that means is that we can take that distance, divide it by 2, and that's going to be the length of our L2. Does that make sense to everybody? So we have to lay that out first, find that distance, and then we're going to use that for half of that for what the length of our crank is going to be. All right. So the length of L2 is going to be equal to that distance between C1 and C2 divided by 2. All right. And then additionally, just like we had before, we know that our L3 is going to be equal to 3 times L2. Okay. All right. So let's take a look at an example that is going to help us with this process. It's also going to help you with the homework problem that you have. So again, since they don't have any examples along the way in the sections of this chapter, we're going to look to the problems to help us with that. So the problem that we're going to do is going to be 519. And then the problem that you're going to have for your homework assignment is going to be 520. Okay, so 519 is going to give you a nice process to go through for this type of a mechanism so that you can use it for finishing up your problem 520. So now you're going to notice that it kind of has that same setup as the section before. So it says for these problems, 19 through 28, design a crank rocker mechanism for the time interval equal to Q. So for both of these, the time interval is going to be 1. Okay, so as we know, when we have a time interval of 1, that means that the motion is going to be symmetrical. So we're going to have the same amount of time going to the extreme position in one direction and then back in the extreme position the other. Okay, and then we're going to notice that our angle, that's what the delta theta 4 here is going to be whatever that value is. So we're up on 19, so that's going to be 78 degrees. That's the total throw angle, the output angle for which that's going to go through. And then the time is going to be equal to 1.2 seconds. Now, what we want to find out is we want to assign what are the lengths 1, 2, 3, 4, and a crank speed. So that's going to be our W. So let's start out our problem like we normally do. And first identify what we know or what we're given, and then what we have to find. So this is going to be problem 519, okay? And we are given Q equal to 1, our change in T cycle. Remember, they're using just T for the total time, as stated up in the problem. But in the chapter, the variable that we've been using for the cycle time is that delta T cycle. And for this problem, the total time is 1.2 seconds, okay? And then we're also given the throw angle is 78 degrees, okay? Now, what do we need to find? Oopsie, find D. Find, okay. We need to find L1, okay. L2, L3, L4, we're gonna have a length for that. And we need to find W2, okay. So the first step that I'm going to do is going to get rid of W2 because like I said, otherwise I go through the whole process, I get too involved in that and I forget about W2. So step number 1, I'm going to take care of that W2 right away. We know that W2 is going to be equal to, if you go back to your equation sheet, this is the crank, a rotational speed, and it's going to be 1 revolution divided by that total time for 1 cycle. So we're going to take 1 revolution, and it's going to be delta T cycle. Don't forget, still applying here, we have to put our equation in variable form first before we put anything else in. Equal to 1 revolution. So the amount of time for 1 cycle is 1.2 seconds. Do not leave your angular velocity. Please don't do that. I'm still seeing that and sprinkled around sometimes where you're leaving your angular velocity for a rotating link, any W's. When you're reporting them, sometimes you're leaving them in revolutions per second or radians per second. Remember, it's a standard to report those out and to express those in RPMs. Always convert those back to RPMs. So I'm going to right away, I'm not even going to worry about calculating this out. I'm going to right away do my conversion of 60 seconds in 1 minute so that I'm now in revolutions per minute. And what do you get for your W2 for this problem? And I'll open up the chat box so I can see. Oops, I see some chats. I'm so sorry. Oh, is it 50? Oh my goodness, you guys are so fast. Yep, that looks correct. Good. 50 RPMs. And then in the room, did you guys get 50 as well? Awesome. Yeah, by the math, it looks like that's going to be the case. Perfect. So we're done with that. So that takes care of W2. Okay. Then step number 2. Okay. We now need to determine the rest of these lengths. Now, when we have length number 4, so L4 for a crank rocker, we're going to assign this by the designer. Okay, so we get to pick that value. So what I've done is I've started in AutoCAD. My value here, what did I use? I used a 4. Okay, so I am going to use that over here. So basically, I have kind of the finished version over here, but I'm going to go through the process with you guys so you know exactly what we're going to do. I'm going to pick that same 4-inch length. This is where you as a designer get the discretion. They're not giving you in the problem what the length of link number 4 is. Okay, we get to pick this. Just like remember in the last problem when we had the offset slider crank, we got to pick theta M. All right, we just have to give it a number. So that's what we're going to do here. So I am going to draw a line, and this is I assigned over on the left hand here A, and then D is going to be my output length. So I'm going to just assign a length here. So I'm going to do this line, and I'm going to start at the center here, and I'm going to draw a vertical line going straight up. So this is in the way, get that out of the way. Perpendicularity. Okay, and I'm going to go along this line. I want it to be vertical, and I'm going to say 4 inches long. Okay, and again, that 4 inches, I'm picking it out of the air, truly. That's all that I'm doing. You could make it 2 inches. You could make it 6 inches. All right, you're just starting with a value, okay? So then on the end of that, I am going to draw a little joint. So I'm going to go from that endpoint all the way up to the top, okay? And that is going to be point C on my 4-bar mechanism, all right? So this is going to be point C. I'm just going to change that. Capital C, there we go. And this is link number 4. So I'm going to grab my link 1. I'm going to copy this over, and this is link number 4. Okay. All right. Now, we are now going to draw the throw angle. Okay, so we're going to rotate, copy this link in the extreme so that we have a throw angle of 78 degrees. Okay, now since this is vertical, and this is again something that we just have to come up with. All right, since this is vertical, I'm going to take half the 78 and I'm going to go on one side and half on the other. You could put the whole 78 on one side, which I actually did on the other one. Okay, this is something that you get to pick. It's not telling us where to start in the problem, so you have freedom here. So you have freedom on the length of the link, and you have freedom on how this 78 degrees is going to be distributed. Okay, so I am going to go ahead. I'm going to do the rotate command. I'm going to rotate. I'm not going to include the circle at the bottom. I just want the whole length of the link and then the endpoint here with C. Okay, so that's going to be that. Now it wants me to know what the base point is. My base point is going to be down here at the base here. Okay. And before I enter in an angle, notice in the command line, this is where I can say I want to leave a copy behind. So I'm going to do C, enter. So now I'm in copy mode and it's going to leave a copy behind. So now if I want to go and I want to put this in one of the extreme positions, I'm going to take 78, I'm going to divide it by 2, and that means 39 degrees is going to be on one side here. So I'm going to enter in negative 39 so that I get to the right here. So I'm just going to negative 39, enter, and that's going to be my first one. Okay. Now I'm going to do that very same thing, and I'm going to now do a positive 39 to go on the other side. So I'm going to do my rotate command again. I'm going to grab those same items there, enter. My base position is going to be down here at its center. Okay. And I'm going to do C for copy, enter, and then I'm going to do the 39 degrees positive. Okay. So I have it looking like this. All right. Now I am going to actually, I don't like that the C's went in kind of an angle. So I'm going to grab my C. I'm going to copy this one over here. The one over on the right is going to be my C2. Okay. And the one over on the left is going to be the C1. There we go. Okay. I'm going to do a quick file save so that I don't lose what I have here. And now I have these in those two positions. Okay. I am going to just change one to the center line, and I'm going to change the other one to just a different color. Oopsie. I'll do hidden, just so that I have 2 different positions, or 3 different positions, if you would. All right, so now the length between here, this is the C1, the C2. I am going to measure that distance, okay? And I'm just going to measure, I'm going to draw a line. I'm just going to use the dimension line. It really doesn't matter which one you use. I just like showing different colors just because then I feel like I can see that difference. Now, if we look back underneath, okay? Remember our condition, sorry, I'm on the wrong one here. Our condition for our L2, the length of L2 is going to be that difference between C1 to C2, that length, okay? Straight line length. And I'm going to divide that by 2, and that's going to be the length of link number 2. So if I go back underneath here, I'm going to add a dimension between C1 and C2, okay? And that distance is 5.035, okay, 5.035. So if I go back underneath here, okay, I'm going to write in here L4 is equal to 4 inches, okay, because we assign that. Assigned, okay. And then L2 is going to be equal to C1 to C2 divided by 2. And that we measured as, I got to remember what it was. It was 5.035. That's what I measured, 5.035 inches. And this is from CAD, okay? I'm going to divide that by 2. And what do we get for our L2? 2.5175. That's what I got too. 2.5, sorry, 175. And that's going to be inches. Okay. So we're going to put a box around this one, box around that one. Okay. And now I'm going to go back to CAD. All right. Now, because our Q is 1, okay, that means that we have the same time going out as we have going in. Just like we did for the sliders, we are going to put A, or the center of rotation of our crank, in line with the path of C1 and C2. So even though C1 and C2 is rotating, we're going to extend this line, the straight line between those two extreme positions, and we're going to extend that out, and A is going to be along that line, okay? So we are going to now do that. I'm just going to draw a vertical line out here, and just a random. And all I want to do is I want to extend this line out to that place. Okay. Now, the other thing that we need to be aware of, we go down here. As you recall, our L3 has to be 3 times L2. Okay. So we know how long L2 is going to be, right? We can now calculate L3. So L3 is going to be equal to 3 times L2, which is going to be 3 times 2.5175 inches. So our L3 you guys get 7.5525. I see some nods of the head. Okay. Now, we also know that, and this holds true because it's the same thing from the previous one, and we could add this down, but we also know that A C2, so the distance from A to C2 is going to be 4 times L2, right? So I want to put our A C2 is going to be equal to 4 times L2, right? And that's from that relationship that we had, previously. Okay, so this one also holds true down here. I'll do that. Actually, I'm going to do this. L2 is not only equal to C1 to C2, but it's also equal to AC2 divided by 4. Okay. So to get that AC2, we're going to take 4 times 2.5175 inches. So my AC2, so it's the distance from A to C2, is going to be you get 10.07 inches. Should all be punching it in? Yeah. Okay. We got some nods. All right. So this is where we're going to know where to place A. Okay. So let's go back to AutoCAD. Now, here's where our C2 is, right? So I am going to draw just a vertical line that I can offset. So I'm going to go here, vertical line straight up. And I'm going to do the offset command. And my distance is going to be the AC2 because I'm going from C2 and I want to find horizontally where that's going to be. And that's going to be the 10.07 inches. Okay. And then I'm going to select this line and it's going to be on the left-hand side. And where it intersects that horizontal line that we created, that extension, that's where our A is going to be. So now I'm going to take and I'm going to move this so that the center of my A is going to be at that intersection. Okay. All right. Okay. Now I'm just going to get rid of this line here. Okay. And I'm going to draw a circle from that center of A, and it's going to be the length of L2. So 2.5517 or 2.5175. There we go. And if I go to, I'm going to use the, I'll use the object line. Line from that center to that quadrant right there. It's a horizontal line. That's going to be the length of my L2. Okay. And then I'm just going to copy my joint here. And it's going to go from here to here. And this is going to be point B. So that's the end point of our length of our crank. So that's going to be point B. All right. Now I'm going to draw this in its outermost position. Okay. All the way out. So I'm going to take my line again from the center there, and I'm going to go all the way over to C2. Okay. So this is where I have my link number 2. So I'm going to label this link number 2. And then this is going to be link number 3 all the way over. Okay. So this is link 2. This is link 3. Okay. And now when I measure these lengths, I'm going to get rid of this radius for right now. I'm going to go back to my dimension. My horizontal line is going to go from there to the center there. And this is my 2.5175 or 2.518. Okay. And then the length of link number 3, which goes all the way from the endpoint of B all the way to C2, because this is where it's all the way out. That length is going to be, should be what we calculated, 7.5525 or 7.553. Okay. That's in the out position. Now, in its back position, I'm going to put that circle back in place so that I can then show my link number 2, and I'm gonna make it the hidden line this time. Back here to there. And that's going to be the opposite position of point B. So we could call the one on the left B1, and we could call the one all the way on the right B2. Okay. I'm actually going to change, I think, these 2 lines to be the center line. I think that's the right thing to do. Okay. Now, you'll notice that we have the C sitting up here, right? So what we're going to do is we are going to take that length of link number 3, which we know to be 7.5525, and we're going to strike an arc so that we can get the position of where it would be here. So this is going to be a radius of 7.5525. So this is the length of link 3. So the intersection with where the crank would be is going to be up here. So it's going to be from its center right there to this intersection. And then this is going to come down here. And then that is going to be position 4, kind of that random place in the middle of our throw. And this is just going to be B. So my white is kind of just like a standard kinematic diagram. The center lines are going to be in extreme position out. And then the hidden lines, I didn't go over the top here with the hidden line, but out over here, this is the crank for the hidden or the closest position on the throw. And then this would extend over the top. Okay. All right. So that is then the process for the crank rocker type of a mechanism to design one of those. Okay. So if we go back and we make sure we have everything identified. So, oh, I know which one I have to do. We have link number 2 identified. Okay, we calculated that. We have link number 3 identified. We calculated that. And then we have link number 4, which was assigned by us. We did that. We started the part with the design with the 4 inches. The only one that we need is this L1. Okay, so let's look at what L1 is going to be. So L1 is going to be, I'm gonna go back along my dimension layer. This is going to be an aligned dimension between the center of A, okay, and the center of D along this way. So it's this length. Do not do a vertical or a horizontal line, okay, or a horizontal dimension. We want to have an aligned dimension, straight line. If we would draw a straight line through that, how long is that? And that is 8.167. So our L1 is 8.167 inches. And this is from CAD. Okay. So if we go underneath here, that L1 is measured from CAD, and it's an aligned dimension, not a vertical or a horizontal. So we have number 1. So it looks like we have everything that we need. So as far as handing in this practice problem and problem number 20, you are going to do the calculations here, just like we saw them through this process. Then you're going to go over to AutoCAD. You're going to draw out your layout with all of the labels. And then you're going to take a screenshot of this, okay? So what I'm looking for really are the confirmation of the dimensions that you either calculated and or used to create your design, okay? Oh, the only other one that we do need is, and I'm going to add that one here, we need the length of link number 4. We know that to be 4 inches, okay? So any questions on this last type of mechanism design? All right. So if we look at the end of chapter 5, okay, the end of chapter 5, right after 519, which is the problem that we just did, the homework problem you have assigned is 520, okay? It is a Q, which is equal to 1. It has a different throw angle here. This one's going to be 100 degrees. And then this time, the time is going to be 3.5. So you're going to go through that very same process, calculating and determining L1 through 4 plus the angular velocity of that link number 2 or the crank, okay? And then creating a diagram using AutoCAD and taking a screenshot of that to hand that in, okay? So, any questions? All right, so right now it doesn't seem like there's any questions. So, so what we're gonna do is I am going to stop the recording here. All right.